Hello, Tensor friends. I got this question the other day. What is the difference between vector calculus and tensor the calculus? And my first reaction was, oh, that's easy. So I started answering it in the comment section. And you know what? It's not that easy to answer. The basic questions are always the most difficult and sometimes the most interesting. So I thought I'd make a short video of how I see the difference between these two things. Okay. Tensor calculus is the form of vector the calculus. In other words, vector calculus is contained within tensor the calculus. Now that's kind of the wordy, easy answer, right? Here's the one that really counts. A vector calculus is coordinate dependent, and tensor calculus is coordinate independent. Now, what do I mean by that? Okay, let's look at an example. Here is the gradient that you've studied in vector the calculus. So it'll show the del operator of a scalar field is equal to the differential of that the scalar field with respect to the coordinates x, y, z times the basis of vectors in Cartesian coordinate x hat, y hat, z hat, or whatever your favorite is, I, j, k. They're all the same. Okay, so this gradient is dependent upon this coordinates, the system you've chosen. If you write this gradient in tensor the calculus, it looks like this. The gradient of that scalar, the field, is equal to the elements of the inverse metric, the tensor, times the differential of that scalar, the field, with respect to an arbitrary, the coordinate, multiplied by an arbitrary basis vector. You don't see any reference here to coordinates. Okay, it's coordinate free. This works in any coordinate, the system. That's why it's a tensor, because it's a tensor works in any coordinate the system. That's the reason we have them. All right. So let's look at what does this actually look like. Let's write it out. Okay. So here's three of the Euclidean the coordinate the systems that we all use. So I've got three indexes, 1, 2, and 3. We're in three dimensions. So you know the Cartesian one. The cylindrical is rho, phi, z. The spherical would be r, the theta, and phi. Okay? So when you expand a generalized the formula like this, and you're working in three dimensions, you have to here to use all the permutations of 1, 2, and 3 in this two index the tensor. So once you decide what you're going to write here, then you see this is a J and this is an I. So you just pick whatever goes with that. Okay. So here's what the whole thing would look like. All right. So we would start with the element of the metric, the tensor, the 1, 1, 1, 2, 1, 3, etc. Then the second row is twos, the second rows are threes. And you can see a pattern here for the differentials 1, 2, 3, 1, 2, 3, 1, 2, 3. And then all of the basis vectors, row 1 is 1, row 2 is 2, row 3 is 3. So there's a pattern here, and you see that, right? Now, since we already talked about the Cartesian, the coordinates, the metric tensor is defined as this. It is the dot product, the inner product of the basis of vectors, okay? So for orthonormal basis of vectors, as you have in Cartesian coordinates, orthonormal, ortho means they're at right angles, and normal means they're unit length 1. The EI dot EJ, inner the product, is called the Kronecker the delta IJ, which is if I equals J, then you got EI dot EI. You know the magnitude of these because they're normal, so it's 1. And the cosine of the angle between them, well, they're on top of each other. So the angle 0, cosine 0 is equal to 1. If I does not equal J, then you still got the magnitude, 1, 1. But the angle between them is 90 because they're orthogonal. So the cosine of 90 is 0. So in this matrix, the looking thing we wrote down here, the only thing that survives is the diagonal 1, 1, 2, 2, and 3, 3. This is 1, 1, and 1. And all these off diagonals, these three and these three are zeros. So it is the identity matrix is what the metric, the tensor is in Cartesian coordinates. Okay? So it only leaves this as 1, 1, 1. And the inverse metric tensor and the metric tensor in Cartesian coordinates is the same because the inverse of the identity matrix is the identity matrix, right? They're all ones. All the off diagonals are zero. So once we write all that down, it just leaves 1, 1, and 1 times what we already had. And then if we say, oh, well, since 1 is x, 2 is y, and 3 is z, then we're right back to where we were when you saw it in vector calculus. So that really is the difference, is that you try to generalize everything, right? Because you want it to be coordinate the free such that it works in all the systems. And this is the breakthrough that Einstein he really made when he was trying to develop general relativity, is trying to get something that described uh, the physics such that it's not dependent upon a reference to frame, because physics has to work in all reference frames. And that's when the story goes. He turned to his math buddy, Marcel de Grossman, who was studying differential geometry and knew about tensor calculus. And so he dug out the book already written by Ricci and Levi-Civita, which described the tensor, the calculus, almost in the format we use today. It was almost exactly like this. And he worked with Einstein, and that's how they basically developed the Einstein field equations. All right, so that is the difference. I hope that helps. See you later.